So far, we have been discussing under the assumption that the two classes, the event and non-event, are of equal importance. But that's not always the case. Take, for instance, you are trying to market to potential customers. Okay? Now, it may be it is very important to be able to identify a potential customer as a customer than it is to identify a non-customer as a non-customer. So in other words, if you have an actual customer and you don't identify that customer, then you lose business, which may be more important than the other error of identifying a non-customer as a customer, where you may spend some time trying to woo the customer and fail, which may be okay, which may not be that important, or in terms of opportunity cost, that may cost you less than not identifying a customer. Okay, there are lots of examples like this. So if you have medical fraud, then it is important to be able to catch a fraud than it is to if you have a legitimate transaction and that gets tagged as non-fraudulent, then you spend more time. There is a cost. So because you then going to research that good case, thinking that it is fraudulent, and then realize that it is a legitimate transaction, and then let it go. The cost there is not zero, but it is much less than if there is a fraudulent case and then you don't detect that, and that fraud may be a lot more expensive than the time that you spend with something that was erroneously detected as an event. So the cost of the two classes, misidentifying these two classes being the same, is not always valid. So unequal importance of classes is an important consideration when we are trying to evaluate performance. Okay, some of the cases here, as I just discussed, so tax fraud, credit fraud, okay, response to promotional offer, predicting delayed fraud, all of these cases, predicting an event correctly is more important than predicting a non-event as an event, which is an error, which may have some cost, but may be much less than the other error. So in such cases, overall accuracy is not a good measure. Okay, overall accuracy means you let everybody. So in the case of fraud, suppose if 2% of the transactions are fraud, 98% are good. So if you use the naive method, misclassification rate, then classifying everybody as good, legitimate transaction will give you very low misclassification error. But then you will not catch any of the non-legitimate transactions. So in those cases, sensitivity and specificity will be much better measures. And asymmetric misclassification. So these misclassifications will have asymmetric costs. Okay, the cost of making a misclassification error may be higher for one class, okay, than another one. The benefit again may be different. Okay, so we have to take those things into consideration. Okay, let's look at an example. Because you have a promotional offer. Okay, suppose that we want to develop a classifier that identifies buyers. Okay, so we have sales offer that's want to mail to 1,000 people and 1% of them accept the offer. So 99% do not. So of the 1,000, 990 and 10, right? So you have a naive classifier. Okay, so that classifies everybody because there is only 1%. So you're going to classify everybody as class 0, right? All of them. And it turns out, suppose if 10% or 1% of them are actually ones, so that means your error rate is 1%. So that's very good. So here there are 1000. So you're going to predict everybody as class 0, right? So then you're not going to classify anybody as class 1. Okay, so this will be 0. So that will be 990 and 10, right? We can put formulas there. So now misclassification rate, and remember it is off diagonal, so that plus that divided by that. So that's 1%. All right, let's now assume that we have a data mining model that we used in the same data, right? So instead of naive model, some other model. Okay. So here the data is still the same, right? There are 990 actual zeros and 1% is actual event. Okay. Of the 1000, and let's suppose that the data mining model predicted 28 events. Okay, so that means the rest of the observations the model predicted as non-event. Okay. Now let's assume that out of that 28, only 8 of them turned out to be actual ones. So that means that many would be erroneous. Okay, so now let's fill out the rest of the confusion matrix. All right, so now if we can copy that formula, it'll, all right, so here see it's diagonal divided by total. So you get 2.2% misclassification rate. So this data mining method is clearly not as good as the naive method, which has a misclassification rate of only 1%. So this one has 2.2%, which is not good. But the problem here is that predicting the class 1, so for misclassification rate to be a good performance measure, the actual class of 0 and 1 must have the same equal symmetric cost benefit. Okay. But that's not the case. So here, suppose if the net profit from an actual 1 is $10 and the cost of making an offer is $1. Okay. So then what's going to happen here? Let's look at the profits that we make. So we are not going to make any profit here because we are not offering the deal at all, right? Because we have predicted them as 0, and there is nobody here as well, so we are not going to make any profit. So the net profit is zero. Now here, okay, so in this case when we predict 0, we are not going to do anything, right? Now but when we predict 1, we're going to make an offer and that's going to cost you $1, right? So this will be minus 20. So there are 20 people who have been predicted as 1 but turned out to be actual class 0. But in the case of these 8 people who are predicted as 1 and they actually turned out to be 1, okay, we're going to make $10 profit out of each of them. So that'll be $10 times that. Okay, now if you copy that sum over here, you get $60 profit. So when we assign the actual monetary outcome for all these predictions, you see that the data mining method is clearly superior to the naive method because we're going to make $60 profit as opposed to 0. So misclassification rate is not good when there is asymmetric monetary outcomes. Okay, now let's look at average misclassification cost. Okay, suppose that if Q sub 1 is the cost of misclassifying an actual C1 as C2 and Q sub 2 is the other misclassification cost, then the average misclassification cost will be, okay, so these are the costs per misclassification and you multiply that cost with the number of misclassification and divide by n, so that will be your average misclassification cost. And then you can use this as the performance measure to compare models and fine-tune parameters. Okay, and again, this is in SAS Enterprise Miner, there is a way to specify these costs, and then SAS will take that information in model building and parameter tuning. And sometimes these costs may not be easily estimatable. Okay, rather you may have a ratio. Okay, misclassifying an actual C1 as C2 is 5 times more costly than the other way around. Okay, so that's a ratio. So that will be a generalized cost ratio. Okay, so you can have like 1 times 5, for example. So 5 times worse than misclassification the other way around. So then we can use that in our, you can use that in our computations. And categorical targets, okay, most often is going to be a binary target, 0 or 1, okay, event or non-event. But there may be occasions when the target is has more than just 2 classes. So when you have multiple classes, so M classes, then the confusion matrix will be like M rows and M columns. Instead of 2 rows and 2 columns, it will be M rows and M columns for each class. And then theoretically, there are M times M minus 1 misclassification possibilities, and each of them will have a cost. And practically speaking, okay, in most decision-making contexts, even if you have multiple classes, there is probably going to be one that is more predominant than the others. So you may still be able to recode them as a binary target.